Hello, today I want to present my course project. It's about using instruction tuning to fine-tuning Quen 2VL model for object detection. And first, I will introduce how to process the COCO dataset, which is a famous dataset that is suitable for vision tasks. And first, considering my limited computational resources, I divided the dataset into a subset which only contains one-tenth of the original dataset, around 10,000 images. And here is a dataset after the first step. And the second step is to convert the original annotations with COCO format into a structured JSON format that contains um, that contains the image paths and the bounding box of objects in each image. And this format is used to build ground truths during evaluation. And my last step is to convert this format into a structured into an instruction tuning format for my model, like this. As you can see, the message here is a conversation pair, and including user prompt and assistant response. The assistant message contains visual tags and for object category and the bounding boxes. This format is used as input for instruction tuning. Second, I want to introduce my training script. Uh, Here, the base model I used is Quen2VL 2B instructor model, basically a 2 billion parameter multimodal language model that's good at following image text instructions. I fine-tuned it using the Swift architecture's built-in LoRa SFT interface to keep everything organized and reproducible. I put all my training settings into this script, and first I adjust these two parameters in my experiment. The LoRa rank and the LoRa alpha controls the LoRa adapter's capability. I compared three settings in total, and another two is freeze VIT and freeze aligner. These two control whether to update the vision and alignment modules in this model. So I already did around five experiments, and all the weights stored here, but I didn't upload them on my GitHub since they are too large. And the third part is about instruction tuning. I think this is the most important part for my project. Here I designed a set of structured prompts to help the model better understand object detection tasks, not just in terms of recognizing categories, but also understanding quantity and spatial relationships. For example, instead of just saying detect objects, I ask the model things like how many cars in the image and what's inside this specific bounding box. Is there anything in this region? And to achieve this, I designed four types of augmented samples, each targeting a specific aspect of visual understanding. And the first augmentation is counting augmentation. So as you can see, the prompt directly asks the model to count the number of objects for each COCO category in the image. As you can see, for example, please count the number of objects in each category in this image. This is my prompt. And this helps the model gain global awareness of the scene beyond just local detections. And I can show you about this. For example, let's check this image. Okay, you can see the assistant response is there are two person, one bicycle, and one motor cycle. And we can see here there are two persons and one bicycle and one motorcycle. And the second augmentation is fully overlapped box. I select a region that exactly covers an object in the image. Then I ask the model whether this region contains any object, and to specify if it's fully overlapped. And this simulates perfect bounding boxes and enhances the model's ability to recognize ideal object boundaries. And I can do some visualization about this. For example, saying I input the bounding box. Okay, and we see here the bounding box are fully overlap the object. And this is another augmented samples for my training. The third one is called partial overlapped. I slightly perturb the original bounding boxes so that they only partially overlap with the object, and ask the model to describe uh, how much how much the object is overlapped, like 5% covered, and this trains the model to handle occlusion and imperfect framing. So this is another example. You can see it doesn't fully overlap because this person is like around, it's mixed up around like 5 to 10%, and they just say like this. It chooses the person, but only 5% was overlapped. And the last augmentation is called non-overlapping. I generate a box that doesn't intersect with any real object in the 8 COCO categories, and ask whether any object is present uh, in that region. And this negative sample helps reduce the false positives and improves the model reliability. And let me show an example. And we can see here, uh, this bounding box doesn't cover any object. You may say it may partially cover this door, but actually the door is not listed in the 80 Coco categories. Last, I just need to choose weight here and use a merge LoRa tool from the Swift architecture to uh, integrate the LoRa adapter weights into the base Quantile model. And for the inference, um, I just need to load the merged model and the test dataset, and this is for the ground truth dataset. So then all the results will be stored into the inference file. Like I will store the image path, the width and height of the image, and the prediction result with the ground truth here for evaluation. So for the evaluation, I used four metrics like uh, precision, recall, F1 score, and the mean IOU. And in the visualization stage, I draw the predicted bounding boxes and the ground truth bounding boxes on each image to show the detection results. Okay, I can choose a image here. Like, um, the model performs reasonably well, and it can correctly identify most major objects and their positions. However, I think there are still some misdetections and false positives. I believe there are some space for improvement, since this is likely because although I add a large number of instruction augmented training samples for my training, with around 50,000 samples, I still only train the model for like 10 epochs, and the model hasn't yet fully benefited from my enhanced data. So I think with more training, the model could gain better spatial understanding and generalize more effectively to more complex scenarios.